Exercise 20A.2 for Year 13 math students. We're going to look at projectiles again. Projectiles obviously when things are projected, and this is an example of that. We've got some object up here and it's going to be fired, presumably at this man over here. And the question is, I suppose, is it going to hit him or not? To model the motion of projectiles then, but this predominantly today we're going to try to use vectors. So just bear that in mind. We're trying to use vectors. And with that in mind, let's remind ourselves of using SUVAT with vectors from the past. So if we did this in year 12, a particle initially, alright, so in this, because it says its initial velocity, I'm writing u equals 3, minus 4. And accelerates at 1, 2. So a equals 1, 2. Find its velocity after 3 seconds. I want a v. So that looks to me like a SUVAT equation. And when you do SUVAT, we've got the s. Have we got the s? Find it. No, we haven't. We've got the u. We want the v. We've got the a, and we've got the t. So we're looking at using v equals u plus at. But we're going to do this as in a vector equation. So v, which is what I want to find, I'm going to keep that actually as v, less like that, equals the u, which is 3 minus 4, plus a, 1, 2, times by 3. Then you can just see, you can multiply this out. 3 1s are 3, plus that 3 is 6. Minus 4 plus 2 3s are 6. I reckon that's 2, so I reckon the answer is 6, 2. 6, 2 is written in I's and J's, but you can see it's the same thing. So I'm going to run a little video for you. So I'll pause this and I'll start the video.
It is high. Using the force of gravity, a 30-kilogram ball will hurtle down the ramp and fire off the end. And when it does, I will be sitting directly in its path. If I get my sums wrong, I'll be killed outright. To calculate how far the ball is going to go, I need some key measurements about the ramp. Little h is 0.8 meters. The angle is 49.1 degrees. So gravity, I know, on the Earth is 9.8 meters per second squared. Interestingly, you don't have to know what the weight of the ball is, the mass of the ball. That's not relevant to how far the thing's going to go. 2 times gravity times the height, 5.5, multiplied by the speed, by 49.1, that will give me a distance of 9.95 meters. But we've got air resistance, there's friction on the ramp as well. What about the wind today? Okay, so the predicted distance is going to be 5.6 meters. That's where I think the ball is going to land. Which means if I set up my deck chair here, I should be able to watch the whole thing in complete safety. Okay, release the ball. And that is the power of the code.
I suppose what you should take from that is the fact that mathematics is able to predict these things. And it says if we model a football as a particle and ignore air resistance, the only force acting on this object is gravity. And we saw that before, and on the last video I said that the weight, this force downwards, and we effectively therefore know that AY was equal to minus 9.8. But we also said that AX was equal to 0. These two things, it doesn't accelerate sideways, but it does accelerate back to the ground. And, you know, that's what this guy basically just did in the video. He tried to predict how far it would travel. We call these projectiles. Gravity, of course, is the only thing that acts on it once it leaves, you know, once it's been kicked or whatever. And we're going to use SUVAT equations, but we're going to do it using vectors. Now one thing you can do with this is, I know we've talked in the past about AX and AY. This effectively allows us to write A as a vector, and it becomes 0 and minus 9.8. So just using our V equals U plus AT or whatever, we can answer questions. A ball is kicked with a velocity given by 6,4. So let's just do this then. V equals U plus AT. So I want the velocity. The U is 6,4. Now I'm going to say my A then is 0 and minus 9.8. In the x direction there's no acceleration, in the y direction it's minus 9.8. Times by t, which is 0.5. So if I just do that, it won't surprise you to learn that V will be 6 there. Because of 0 times by anything is 0. This effectively becomes minus 0.9 because it's 6 minus the 4.9 we get by doing this sum. And that's my answer. 6 in the x direction minus 0.9 in the y. What's the displacement? Again, s equals ut plus a half at squared. Now what have we got here? We've got s, which I'm after. U I know is 6,4. My t is 0.5 plus a half of 6 came from 0 and minus 9.8 t squared, 0.5 squared. And I can just do the top line on my calculator and then do the bottom line. So I'm going to do 6 times by 0.5 plus a half of 0 times 0.5 squared. And it won't surprise you to learn that last bit didn't make much difference. It was 3. It will make much more difference on the next one. 4 times 0.5 plus 0.5 times negative 9.8 times by 0.5 squared. I've got 31 over 40 or 0.775. Now, I don't know what the answers are. Let's see what I get. They are right. Bang on. So, good. Next example then. The ball is kicked from level ground with velocity u equals this. The ball is intercepted on its way down at a point P, 0.7 meters above the ground. Alright, so it hits here. Or rather, it's caught here, or it hits the crossbar or whatever, hits someone on the head. Modeling the ball as a particle, find the time taken to reach P. Well, of course, I know something about S. And I suppose there are going to be times when I'm going to do this, but let's just try to do this. I think this is, let's just think about, S is something I want to know at the time, is something I want to know as well. S-U-V-A-T. Well, I always know the A. The U I know, I want this, and I want the time. It's the V I don't think I care about, so I think this is S equals UT. It felt as if it was, plus a half AT squared. Now, if I write this out as S, I know it's 0.7 high, but I don't know, so I'm going to write X, comma, not comma, in a vector X and 0.7, equals 3 and 5.6 times T, which is what I'm after, plus a half of A, and I've already shown you the A vector is 0 and minus 9.8, times by the T squared. Now this top line will tell me how far it goes. The bottom line will tell me how high up it goes, and I'll know it goes from 0.7. So just looking at that line, I can write 0.7 equals 5.6 T minus 4.9 T squared. Now, moving everything on one side, I get 4.9 T squared minus 5.6 T plus 0.7 equals 0. And I can chuck that into my calculator. And that was just looking at the Y part of it, the Y component. So menu, go down to A. So I want polynomial coefficient of degree 2. The numbers are 4.9, negative 5.6, and 0.7. And I get answers, T equals 1 and 1/7. Alright, that's interesting. Now T equals 1, presumably, well, you just got to be aware of this. I've got two answers, T equals 1 and T equals 1/7. Obviously 1 is the bigger of the two numbers. And you'll notice on the picture it goes up and it's coming down again. So I think the answer is the second one of the two, T equals 1, the bigger number of the two. The speed and direction of travel at this point. So if I'm going to get the speed and direction of the particle at this point, the football at this point, I think I need to know something about Vx and Vy. I think I need to know this velocity vector. And interestingly, it was the one I didn't find before. So I'm going to write out that equation. So if you remember, we had, SUVAT. And I'm going to ignore this one this time. This one was, what was it, 3 and 5.6. I think I want this one. The A I know is 0 to minus 9.8. And importantly, the time was 1 second. So just using that, I think I get V equals U plus AT is my equation I'm going to use. So my velocity vector is U plus A times by T. And that gives me, I think, 3 and what's 5.6? 5.6 minus the 9.8 effectively. Oh, minus 4.2. Should have just done it in my head. It would have been a lot quicker than trying to do it on my calculator. So that's my velocity vector. Notice what that means. It means at that point in time, it's going across with a speed of 3, then going down with a speed of 4.2. Now, a bit like a lot of vectors, to find the speed, you have to find this using Pythagoras. So the speed is the square root of 3 squared plus 4.2 squared. I'm going to do that now. Menu 1. 9 plus 4.2 squared is that, and then square root the answer. I get as a decimal 5.16 meters per second. It also said the direction. The direction usually you give to the angle to the horizontal. So I'm going to call this theta. So I reckon tan theta is 4.2 divided by 3, opposite over the adjacent. So therefore this inverse tan of 4.2 divided by 3 is 54 degrees. And you describe that as being 54.5 actually degrees below the horizontal. Let's see what it says. 1 second, I got 1 second. 5.16, that's perfect. My last example then, a golf ball rests on level ground and is given a velocity of 2.5. Show that the time taken for the ball to reach its maximum height is 5 over g. That's interesting, they want it over g. So just quickly looking at it, I think this is a V equals U plus AT question. The V, whatever the V is in the x direction, we actually know what it is, but we don't need to worry about it. But I do know that the velocity for it to reach its maximum height, Vy is 0. So you can see that's why I put that as 0. That equals U plus AT. Now normally I'd write A to be 0 and minus 9.8, but they've actually got G, so it's just 0 and minus G instead. Time is the time, that's what I'm after. So just looking at the bottom equation, that's what I'm after. 0 equals 5 minus GT, or GT equals 5, or T equals 5 over G, which is what they had. So that's the first part. Find the speed and the direction after 0.4 seconds. So to do that, of course, well, it's up here somewhere. And I showed you last time, to get the speed, I need to know about Vx and Vy. So at that stage, let's do then, what is it? I think this is V equals U plus AT again. I want my V, so I'm just going to write that as V. Equals U 2.5 plus 0, or minus 9.8 this time, times by 0.4 seconds. So this will equal 2 and 1.08 if you do it on your calculator. Now, again, we do a similar thing. We say that means it's going 2 and 1.08. So you can use Pythagoras to get the speed. Speed is the square root of 2 squared plus 1.08 squared. And we can work out the angle, theta, by doing the inverse tan of 1.08 divided by 2. Now I'll leave you to type those into your calculators, but according to this, it says it's 2.27 and 28.4 degrees. So have a look at that and see if we've got those right. I don't know if we have or not. In class, we're going to have a look at the textbook. We're going to use the Suvat equations with vectors and only these particular questions this time. But these are SUVAT projectiles with vectors, so a very specific set of questions. Good luck.